During the Second World War, one of the biggest deciding factors in entire war campaigns were radars. A radar station that could spot incoming bombers an hour before they arrived gave you time to scramble fighters, position anti-aircraft batteries, and intercept the enemy before a single bomb landed. Without it, you were simply waiting to be hit. Britain understood this earlier and more seriously than almost anyone, and it built an entire early warning network around the idea, a chain of radar stations along its coast that gave the Royal Air Force just enough warning to survive the opening months of the war. This system was called Chain Home. It could detect large formations of incoming aircraft from over 100 kilometers away, which was more than enough to get pilots into the air in time. But Chain Home had a problem baked into its physics. It ran on very long radio waves, which meant it needed enormous antennas, towers over 100 meters tall. And even then, it couldn't make out fine detail. And it definitely couldn't be shrunk down to fit inside a fighter plane or a ship. That changed in February of 1940. Two physicists at the University of Birmingham, John Randall and Harry Boot, built something that changed the entire war, the cavity magnetron. It generated microwave power at a level roughly 100 times beyond anything available before it, in a device small enough to fit on a tabletop. Inside the magnetron, a heated central cathode releases a cloud of electrons through thermionic emission. Heat literally knocks electrons loose from the metal surface. Normally, those electrons would fly straight outward toward the surrounding anode, but the magnetron places a strong magnetic field perpendicular to that path. And a magnetic field doesn't speed up or slow down a moving charge. It bends its direction. The force is at right angles to both the electron's velocity and the magnetic field, which is exactly the condition for circular motion. As the electrons spiral past the ring of resonant cavities surrounding the cathode, each cavity acts like a tuning fork. It has a natural resonant frequency determined by its physical size, the same way a wine glass rings at a specific pitch when you flick it. The passing electrons excite that resonance, and the cavities convert the electron's kinetic energy directly into a coherent, high-power microwave wave. That wave gets pulled off through an antenna, and you have radar. Britain couldn't manufacture these fast enough. So that September, a British science mission flew to the United States carrying one of the most valuable objects of the entire war, a working cavity magnetron. The contract for mass production went to a company that today you'd recognize for something else entirely, Raytheon. And the man who figured out how to manufacture magnetrons by the thousand was a self-taught engineer named Percy Spencer. By 1945, Spencer had redesigned magnetron manufacturing so thoroughly that daily output went from 17 units to 2,600, and Raytheon was producing roughly 80% of every magnetron used in American and British radar. One day in 1945, Spencer was testing a magnetron when he felt something strange in his pocket, warm, then wet. His chocolate bar was melting. Most people would assume the lab was just warm, toss the ruined candy, and move on. He knew the room wasn't hot, so he treated the melted chocolate as a piece of evidence and ran the obvious next experiment. He sent for a bag of popcorn kernels and held them near the magnetron. They popped with no flame, no heat source, just an invisible field. Then, by some accounts, he placed a raw egg nearby, and it reportedly cooked and burst from the inside. That detail, cooking from the inside rather than the outside, is the first real clue toward the actual physics, and we're about to take it apart properly. Here is a water molecule. 2 hydrogen atoms and 1 oxygen atom, bonded at an angle of roughly 104.5 degrees. That gives the oxygen end of the molecule a slight negative charge, and each hydrogen end a slight positive charge. If water were a straight line, HOH at 180 degrees, those two charge poles would cancel out perfectly, and water would be a nonpolar molecule, like carbon dioxide. But because the molecule is bent, the charge poles don't cancel. They add up to a net separation of charge across the whole molecule. what chemists call a dipole moment. Now bring in an external electric field, say from a microwave. That field exerts a torque on every one of these little dipoles, trying to twist them into alignment. If you were in a vacuum, a water molecule could just snap back and forth and nothing much would happen. It would absorb and re-emit the energy with nothing lost. But liquid water is crowded. Every molecule is jostling shoulder to shoulder with billions of neighbors. So instead of rotating cleanly, the molecules wrench, collide, and drag against their neighbors as they try to follow the field. That dragging at the molecular scale is friction. And friction converts kinetic energy into heat. The exact same principle as rubbing your hands together, just happening roughly 2.5 billion times per second. This is called dielectric heating. This also quietly explains something a lot of people have noticed but never quite put together. Ice barely heats up in a microwave, even though it's made of the exact same water molecules. In ice, those molecules are locked into a rigid crystal lattice, hydrogen bonded into fixed positions. They can vibrate slightly in place, but they can't freely rotate to chase the flipping field the way they can in liquid water. Less rotation means less molecular friction, which means dramatically less heat, which is exactly why frozen food famously heats unevenly, with liquid pockets racing ahead while solid ice barely budges. But Raytheon moved fast. They filed a patent in October 1945, just months after the chocolate bar melted, and within 2 years had a working commercial product, the Radiarange. It stood about 1.7 meters tall, weighed 340 kilograms, needed a plumbed water cooling line just to keep the magnetron from overheating, and cost the modern equivalent of well over $50,000. This wasn't a kitchen appliance. It was industrial radar hardware wearing an oven's clothing, and the very first unit went into the kitchen of one of Raytheon's own founders, where it apparently ran for 3 decades. The remaining problem wasn't science anymore, it was pure engineering and economics. How do you take an industrial-grade, water-cooled device and shrink it into something that fits on a countertop? The first attempt came in 1955, when Raytheon licensed the technology to Tappan, a stove manufacturer. Their home unit retailed at $1,295, about $14,000 today, and still needed water cooling. Almost nobody bought one. In 1964, Sharp introduced the first microwave with a turntable, solving a real problem rooted directly in the physics we just covered. Inside a metal cavity, microwaves don't fill the space evenly. They bounce and interfere, creating standing wave patterns with hot zones and cold zones. This is a direct consequence of wave interference. Where wave crests from different directions overlap, you get a hot spot. Where a crest meets a trough, they cancel, and you get a cold spot. A turntable doesn't fix the standing wave pattern. It just drags your food through every hot and cold zone in turn, averaging out the unevenness over time. The real turning point came when Raytheon's newly acquired subsidiary, Amana, released the Radiarange RR4, the first genuinely compact countertop model, priced at $495. And once price and size cleared that threshold, adoption took off close to exponentially. By 1975, microwave ovens were outselling gas ranges in America for the first time. By the mid-1980s, they sat in over half of all U.S. households. By 1997, that number reached roughly 90%. There's a pattern worth naming directly because it shows up again and again across the history of technology. The cavity magnetron wasn't built to cook anything. It was built to help a nation under nightly bombardment find aircraft in the dark. Nobody funding it in 1940 was thinking about chocolate bars or popcorn. But once you have a genuinely new capability, people inevitably find uses for it that the original engineers never imagined. And it's worth remembering the next time you reheat leftovers in 90 seconds that the box doing it is the direct descendant of a piece of hardware designed to win a war, repurposed by one curious engineer who refused to just throw away a ruined candy bar. If you want to see more deep dives like this, subscribe, because there's more of this on the way. Thanks for watching.